So last week we introduced the issue of chemistry, and that is the desire for everything that exists to become the ideal. And we described the ideal as to have all of an element or a compound or whatever to have all of their valence electrons full. And the way we described that was the column 8A. If everything was just like column 8A, we decided. Everybody wants to be like column 8A. Oh, they're just the best in the world. Everybody admires column 8A. And so, everything known to man does its best to look like column 8A, and that is to have all of its valence electrons filled up. So we introduced that concept last week, and is there any questions about that? Because again, going forward, there's not a lot of chance that you're going to get the rest of this stuff if you don't get that. So are we good with regards to that? Do we understand that that's what everything wants to do? Now, the next question, and what we're going to answer today, is how does it do that? How does everything known to man do that? All right? And that's what we're going to look at today. So if there's not any questions, would you turn to page 2 of your notes? And we'll start off right there. All I got to do is find page 2. Let's see here. Well, that's great. That's not what I want. All right. Why do I have module 6? All right, at the top of page 2. If you turn to page 258 in your textbook, there is the definition of ionization, and then sadly I'm going to have you write them. But again, ideas or principles that you need to remember, well, be familiar with, okay? So if you write it, perhaps that will help you. Perhaps. Is that, yes?
I wasn't here last week, so
Okay.
I don't have any terms or anything. Do you have an extra sheet?
Ooh, let's take a look. I think I do. Let's see. Oh, that's AMP. Uh-oh. Uh-oh. Son, would you do me a favor? Would you take your notes down to the, I don't know who's there today, but ask her to make a copy of each one of those pages, please. Thank you, son. I'm grateful. So you'll have one in just a minute. Thank you for speaking up. It's hard to follow along if you don't have the goodies. Okay, so ionization. The process by which an atom turns into an ion by gaining or losing electrons. So the first thing that we're looking at, and again on page, you know what, I'm on page 3. Sorry about that, guys. Like I say, when it's harried in the morning, you know, it gets started this way with terrible traffic, but anyway. Top of page 2, all right? I was on page 3. In ionic compounds, nonmetals try to gain electrons so that the Lewis structure has 8 dots around it. So last week we talked about Lewis structure, and all that is a way to describe the valence electrons of a particular element, and then we'll put the elements together into compounds. The Lewis structures simply say how many valence electrons are around a given element, and that's not good. And the way that you determine that, as we explained last week as well, is by looking at your handy dandy periodic table. If you would take a quick look. Yes?
No one's down there.
No one's down there? Oh man. All right. Could you, there is a copy machine on top of on top of, you know how to make copies? I don't think you've ever made copies in your life, have you?
I can just get someone to send me a picture.
Well, but you need to be able to follow along. Aha!
I got studies all of them.
Oh, you do too. Could you make a copy, one copy of, there's two-sided, but could you make a one copy?
One copy. of
Yes,
this.
thank you so much. I'm gonna teach you how to make copies, son. How is that even possible? All right. Gonna be a wild day today. So here's your periodic table. Here it is, right here. So we're talking about columns 1A and 2A and 3A through 8A is the chemistry that we're really looking at in terms of this course. And especially with regards to what happens to these various elements in combining and getting towards, because some of them will never reach it, but getting towards the ideal, and that is 8 valence electrons. The exception, of course, is hydrogen sitting there at the top. It wants 2. It wants to be able to either receive or share 2 electrons. So, just pick any number here in the periodic table. Let's pick oxygen. All right, so here's oxygen. And we know immediately by virtue of these columns and their numbering how many valence electrons they have. Oxygen's in the 6A column, so we know it has 6 valence electrons. And the way that you display that is you start to the right. 1, 2, 3, 4, 5, 6. Okay, so there is a Lewis structure. The other name for that sort of thing is called an electron dot diagram. Kind of like that better myself, but anyway, Lewis structure or electron dot diagram. And we introduced that the last time, and that again is going to be important in terms of where we're headed for the rest of this module especially. So, in ionic compounds, non-metals, remember what an ionic compound is? It's the combination of a metal and a non-metal. The metals are everywhere to the left of the pink stair step, and the non-metals are everything to the right of the stair step. In other words, everything in the pink, and that also includes hydrogen over here to the side. So, in ionic compounds, non-metals try to gain electrons so that their Lewis structure has 8 dots around it. So everything in the pink here, you know, with regards to its relationship with other ions, is that it's demanding. I want your electrons, says the non-metals in the pink. All right? That's what they're going to do. They want electrons. However, in ionic compounds, metals try to lose electrons until their Lewis structure has no dots around it. In other words, they're the ideal by losing electrons. So they go, okay, fine, you can have my electrons, because that's what I want anyway. And the non-metals say, yeah, that's what I want your electrons. And the metals say, okay, you can have them, and now we're all happy, okay? So we reach 8 valence electrons either by receiving electrons or by donating them. Atoms join together in such a way as to make sure that they all end up with the ideal configuration. It's all about reaching the ideal in the 8A column. All right? That's what everybody wants. Atoms, that is in metals, give up an electron and become positive. So if you think about it, you have an equal number of electrons and an equal number of protons, so you're electrically neutral, right? But if you got something that's given up electrons, all right, you're going to become slightly positive, right? Well, the same thing with regards to the nonmetals who receive those electrons. The nonmetals that gain an electron become negative and are listed as negative, all right? So it's whatever something is minus. All right? And an ion, let's define it. We actually got to go backwards a little bit in terms of this. Yes, sir. Oh, how about that? I didn't see it. And I didn't even get a chance to thank her. That was nice. There you go. Oh. There you go. All right. There and there. All right, let's just do it the easy way. Let's go to the back. All right, an ion is an atom that has gained or lost electrons and thus has become electrically charged. Would you please write that in your little notes there? An ion is an atom that has gained or lost electrons and thus has become electrically charged. That's a nice way to put it, isn't it? All right? An atom that has gained or lost electrons and thus has become electrically charged. So, positive ions have the same name as the atom from which they came from. All right? So, and we know the positive ions are the metals, right? That's what we just have been discussing. The metals want to give up electrons. They do, and so they become slightly positive. And so when you name them, you start with that name, and it's the same name for whatever you have. So it's hydrogen, well, not necessarily. It's lithium something, it's beryllium something, it's sodium something, magnesium something. All right? Negative ions have an "ide" suffix added to the name of the atom from which they came. So now we have an explanation of the naming that we did several modules ago, right? So as it turns out, everything in the non-metal category gets named secondly, and you add the "ide" suffix to it. So those that receive become slightly negative, and you add the "ide" suffix when you're naming it. Ionic compounds get their chemical formulas when atoms start exchanging electrons until all of them attain the ideal electron configuration. So we just said it again, didn't we? And that's the Hebraic method, right? Repetition. Maybe eventually I'll understand it, and so you will too. But if we repeat it over and over again, the idea is that we'll get it. What everybody wants is the ideal configuration, 8 valence electrons. Once they achieve this, they're attracted to one another because of the electrical charges they have gained, positive attracted to negative, which holds ionic compounds together. So, in the instance of magnesium, say you're going to bond with sulfur. Take a look at that, because this is actually where we're going with this. Take a look at your periodic table, please. Pull it out and look, or turn to the front page of your textbook. So look at number 12. All right. So what does number 12 want to do? What does magnesium want to do? Who wants to tell me what magnesium wants to do? Yes.
It wants to lose 2 of its valence.
Thank you very much. It wants to lose 2. Now, look at sulfur, number 16. All right? What does sulfur want to do? It wants to go to the dance. Everybody wants to go to the dance. What does sulfur want to do? Go ahead, please.
It wants to gain 2 valence electrons.
Beautiful, exactly. I think we have a match made in heaven, right there. Oh, I want to give you my 2 electrons. And sulfur says, oh, that's what I've always wanted, was 2 electrons. And so the electrons go dancing away from the magnesium over to the sulfur. What we have is a slightly positive magnesium and a slightly negative sulfur, and voila, we come together. Oh, they didn't even have to get on Match.com. It's just beautiful. It's a beautiful thing, isn't it? But that's the way it works. That's the way it works with an ionic compound, all right? There's no bonding. Ooh, we're going to find out about bonding in a minute. Bond, the bond that can't be broken. There's attraction in ionic bonding or ionic compounds, positive to negative, all right? Is there questions about that so far? Let's look at the rules. Yes, there's rules. There's commandments. We're going to get legalistic on you. There's rules for ionic bonding. And here they are. I've got them listed for you. They are, here, they're listed on page 255 for you, okay? But I had written them for you in your handy-dandy little notes. So, atoms in the 1A column have one valence electron and they want to lose it, all right? So they become +1, all right? So the 1A column, everybody there wants to lose it with the exception of hydrogen, and it kind of plays the game. It kind of plays the field, all right? Because sometimes hydrogen will bond in a ionic way, and sometimes it will bond in a covalent way, and we'll see that, and well, we'll sort of see that. I'm just kind of giving you that as an extra. So everything in 1A, for the most part, wants to lose one electron. How about 2A? We just found that out, right? Everything in 2A, everything in column 2A, helium all the way down, magnesium, calcium, they want to lose 2 electrons, and when they do, they become +2. In column 3A, boron is a nonmetal and it differs from everybody else, all right? Boron had to be different. You gotta be different. It's a nonmetal. The rest of the metals, they want to lose 3 valence electrons and become +3. With boron being the exception, what does boron want? Tell me what boron wants. Tell me what you want, what you really, really want. I tell you, that's about as aging me. Tell me what boron wants, what it really, really wants. Count them up. 1, 2, 3, 4, 5. It wants 5 electrons for the most part. All right? Column 4A, calcium and silicon are nonmetals that want to gain 4 electrons. All right? Calcium and silicon, but look at the rest there. For the most part, the rest will want to give up 4 electrons. All right? The metals. Column 5A is mostly nonmetals, and they want to gain 3 electrons. You see how it's working? So there's column 5A, nitrogen, I think that's phosphorus, isn't that phosphorus? Thank you very much. And astatine, they want to gain 3 electrons. And when they do, what happens? It's ideal. Oh, everything is so good. Column 6A, mostly nonmetals that want to gain 2. And finally, column 7A, they want 1 electron. All I need is 1. Just give me 1. Somebody's got 1 electron. Give me 1 electron. If the charges have the same numerical value, then the subscript for each one is 1 and therefore can be ignored, such as barium oxide. So in terms of, well, where in the world is barium? Where did it go? Anybody see barium out there? It is. Column 2A, number 56. And we see that it wants to give up its 2 electrons, just like we discussed with magnesium sulfate, sulfide, I guess, for our description. But in terms of barium oxide, we see that oxygen wants 2 electrons, barium wants to give up the 2. So you have a +2 and a -2. And because of that, you don't have to list the numbers, all right? That's the way it works. However, if the charges have different numerical values, what you're going to do is drop the plus and minus signs and switch to numbers and use them as subscripts, okay? So in terms of the way this is working, if it's differing in the numbers, you're gonna list the numbers, such as aluminum sulfide. Look at aluminum sitting in column 3A, all right? It wants to give up its 3 electrons. Sulfur only wants 2, all right? So you've got an uneven situation there. So what has to happen? We have to group more atoms together in order to make it equal in terms of the total number of electrons that are shared. And in this instance, sulfur, there's got to be 3 of them, and aluminum, there's got to be 2 to get the numbers correct there. And in terms of this, take a look at page 254, and you get an idea in terms of the way that magnesium and fluoride come together. So look at, once again, on your periodic table, all we're doing is sort of familiarizing you with this stuff. We keep going over it and over it. But magnesium's sitting in the 2A column, right? So it wants to give up 2 electrons. But look where fluorine is. It's in the 7A column. It only wants to receive 1, all right? You can't give me 2. I won't be ideal if you forced me to take 2. But what if we invite another fluorine in here? Hey, come on. He's got an electron to give. And so that's what happens here. Magnesium gives up its 2 electrons, but in this instance to 2 fluorines. And what happens then is everybody's happy. All right, we come together in terms of the electrical charges. We're attracted, the 2 fluorines are attracted to the magnesium, and vice versa. The magnesium's attracted to the fluorine. There's exceptions to the way these things work. Almost always the exceptions are in the metals. All right. Groups 1B through 8A, in other words, the middle part of the chart, the yellow transition metal region, does not follow standard rules. And so as an introductory course, as a first chemistry, high school chemistry course, we're just not going to deal with that. The metal's positive charge, metals want to give up electrons, as we've discussed, is stated in the ionic compound's name with a Roman numeral in parenthesis. So in terms of exceptions, and I'm just going to refer you to the example in your notes, and you can look at these things too. Where is it? Discuss exceptions. There we go. Page 257 if you want to read through this. But the point is, metals do funky things. And tin, SN, number 50, notice it's in the 4A column. Well, sometimes it just wants to give up 2 electrons. I don't know why, but that's just the way it works. And when it does behave in a way that's contrary to the rules that we just discussed, you have to label it as such. And in this instance, sometimes tin just gives up 2 electrons, and it's tin 2 chloride in this instance if it bonds with chlorine. In other words, there's a chlorine atom that receives 1 of those 10 electrons, and then there's another. The reason the exceptions must be named this way is because they can have other charges. Tin 4 chloride. So sometimes they want to give up all 4 electrons. All right, so that's just the way it works. Exceptions are stated to be exceptions because they are, and in terms of you being responsible there, you'll be flagged to that. All right, or just at least be familiar with this exception in your notes. All right, let me pause there and see if there's any questions. Any questions? We got a lot to do today. As you well see, there's 5 pages of notes. It's entirely possible that we're not going to reach 5 pages of notes, but fear not. All right, we will finish the lecture if we have to next week, and however far we get will be how responsible you are for the notes. I just want to be sure you get this chapter because it is, they're all important, right? But it's important to build on this chapter. So if we need to take a little bit of time next week, we'll do that to be sure we get it. Turn to page 258. There's our ionization, as I tried to start you this morning. So ionization is the process by which atoms an atom turns into an ion by losing and gaining electrons. So ionization is simply the process of becoming an ion, right? Either losing or gaining an electron. All right, that's ionization. Now, ionization potential, please write this down. The amount of energy needed in order to take an electron away from an atom. Give me your electron. That requires energy, all right? Even though an atom wants to give up its electrons, it still takes energy to do that, all right? So the ionization potential is the definition, is the term for that. How much energy do I need in order to take your electron, all right? How much energy? Now, there is a handy-dandy graph to tell us about that. Let's do the definition for periodic table first, and then we'll read the notes from ionization potential through to periodic table. But please write down periodic table. Just characteristic of atoms, periodic property, excuse me, that varies regularly across a periodic chart. So a periodic property is what we're going to look at here in terms of ionization potential and electron negativity and diameter or radius of atoms, but we'll get to that in a second. So periodic property, a characteristic of atoms that varies regularly across the periodic chart. Did you write that down? Did we get it? Good. Above that, for atoms that hold on to their electrons tightly, it takes more energy to take an electron away compared to those who hold them loosely and require less energy to remove them. All right? So it just makes sense, right? If you've got an atom that that wants electrons, it's going to hold on to the ones it's got with a lot of ferocity, right? You can't have my electrons. No, I want yours. All right? But I've got all of this energy that says, I'm going to take them. All right? Uh-oh, I lost Grant. Uh-oh. What happened? What happened? Aaliyah Goldman. Oh, how about that? All right. Let's see. Well, dumb thing. Admit. Is it going to work? Let's see. Hey, Aaliyah. How are you? We lost Grant, though. You doing okay?
Sir.
Good, good. So, we're moving right along. We're on page 3. So, you got questions, you know the drill. Just holler at me. Alrighty. So, obviously, if you're in column 7A, it's going to take a lot of energy to take your electrons, all right? But what if you're in column 1A? Is it going to take a lot of energy for you to give up your electron? No, because you want to give it up anyway. I'm taking your electron. Okay. Okay? So that's pretty much it. Doesn't take much energy to remove the electrons from column 1A or column 2A for that matter. Atoms in group 1A have a low ionization potential. It takes little energy to remove their electron because they want to lose it to get to the ideal. Atoms in 7A have a high ionization potential. It takes a lot of energy to remove their electrons because they want to add one in order to get to the ideal. In general, the ionization potential of atoms increases from the left here we go. From the left of the periodic chart to the right, all right? And as a matter of fact, rather than looking at me, turn over to page 260. There's our handy-dandy picture. We love pictures, right? So there it is. Ionization potential generally increases from right to left, all right? Again, because it takes a lot more energy over here to get that electron out of something that doesn't want to get it up than it does from this column. And ionization potential goes from the top to bottom in terms of decreasing. You know, that graph, when I first saw it, I always thought that was kind of confusing. You know, why don't you have increasing on both of them? All right, one's decrease and one's increase. Well, So if you wanted to write red in red and point the arrow up, all right, ionization potential is higher up here than it is down here. In other words, it's easier to take electrons down here than it is up here. And why, pray tell, would that be? Well, the answer is given to you right there in your notes. Atoms near the top of the periodic chart hold on to their electrons more tightly than those at the bottom. In general, the ionization potential of atoms decreases from the top of the periodic chart to the bottom, or increases from the bottom up. All right? This is so because the valence electrons on the lower energy levels are closer to the nucleus and feel the positive attraction of the protons more. The valence electrons on the outer energy levels feel the positive attraction of the protons less, and so they're more likely to give up their valence electrons. So again, in terms of the attraction, the positive, negative, protons to electrons, positive to negative, it's felt more closer in to the nucleus, right? And that's what we're talking about in terms of these atoms at the top. The further out you go in orbitals, all right, further away, then you're just not feeling it. I'm not feeling it, all right? I'm just going to tell you, I'm not feeling it, all right? Says the atoms lower on your periodic chart. All right, what do we think about that? Isn't that just the coolest stuff you've heard all day? Of course, it's early. You're liable to hear cooler stuff as the day goes on. So are we okay? You understand what that stuff is? It's impossible not to understand the graph. Electron negativity. It's very similar to the ionization potential, but different, all right? Electron negativity is a measure of how strongly an atom attracts electrons to itself. So, ionization potential had to do with the amount of energy necessary to separate an atom's electrons. Electron negativity is how strong is that attraction? How strong is it? All right? Ooh, it's really strong. Ooh, that particular atom is really, really attractive. Oh, yeah. So, what are we talking here? What about column 7A? How is its electron negativity high or low? What do you suppose? Hello. Hello. Column 7A really wants an electron. All right? So it's obviously going to have a high electron negativity because it's the measure of how strongly the atom is attracting electrons to itself. What about column 1A, the other extreme? Excuse me, the other extreme. It has no desire whatsoever to attract electrons to itself, for the most part. And so its electron negativity is going to be pretty small. All right? So if you'll notice again the way the ionization potential and electron negativity work. Ionization potential and electron negativity increase left to right. Again, makes sense, right? And in the same way, ionization potential and electron negativity decrease, and for the same reasons as well. As electron, I'm reading from the bottom, page 3. As electron negativity of an atom increases, its desire to become a negative ion increases, okay? And so, again, that just makes sense, right? The further we go over to the side here, the more it wants to receive those electrons and therefore become slightly negative because it's got more than the original number of electrons. In general, the electron negativity of atoms increases from left to right on the periodic chart. Group 1A has little desire to gain electrons, and so it has less electron negativity. Group 7A has a lot of desire to gain electrons, so they have greater electron negativity. In general, the electron negativity of atoms decreases from the top to bottom on the periodic chart. Energy levels closer to the nucleus and the atom's protons add more attraction than those energy levels further away. So that's still the same situation. So what do we think about electron negativity? Does that make sense? Slightly different definition. We're just talking about really two peas in the same pod, okay? Any questions? Going to keep moving. Even though atoms, I'm on page 4 of your notes at the very top. Even though atoms have complex shapes due to the shapes of their orbitals, we can approximate atoms as tiny spheres, making its radius an indication of its size. So remember, we discussed the pear-shaped p orbitals, all right? And we talked about the s orbitals in terms of the spherical shape that they were. But remember also, the electron can be anywhere in that sphere or anywhere in that pair, remember? Well, in terms of discussing its radius, we can look at electrons, as atoms, pretty much as just as spheres, all right? We can discuss it that way. Again, the electrons take different directions, different shapes as orbitals, but in measuring its size, its radius, all right, so we got this number going on here. Remember, we got that, we got this, we got that, we got this, we got that, and we got this, something like that, all right? And then we got this, and we got that, and we got that. All right, but in terms of measuring its radius, remember that's the middle to the outside, we can just view the whole thing as a sphere. And we can measure that too. Oh, that's where the top went. Yeah. We can bring it back to life. There we go. Back to your notes. In general, the atomic radius increases from the top to bottom. Makes sense, right? We're getting further out in terms of energy levels, all right? There's 1s, 2s, 3s, and out we go, all right? So it generally increases that way. Moving from left to right on the periodic table, however, does not change the energy level. However, moving left to right, terrible, moving left to right, all right, finds increasing atomic number, all right? So, again, if you're looking at your periodic table on the 4th energy level, you start at potassium and you're moving all the way across. When you reach 35, you started on the 4th energy level at number 19. When you reach number 35, you're talking 35 protons, 35 electrons versus 19 in potassium, all right? So you've got more protons, which means what? It means more positive charge, more positive attraction and in the nucleus, and it means greater electrical force on the electrons, pulling them closer. So again, if you'll turn one more page for a pretty little picture, look at that diagram, and it just shows you what we're talking about. The atomic radius decreases as you go left to right because you got more protons to attract those electrons, and they come in a little bit, all right? So the radius on energy level 1, or let's talk about 2 because there's more there. The radius of the lithium atom is going to be larger than that of the fluorine atom because, again, the attraction of the protons. All right? In general, the atomic radius decreases from left to right on the periodic chart. So, is there questions about that? Does that make sense? Man, we're right to the end too. I'm gonna do you 2 more minutes just so next time. I thought this was going to happen. We weren't going to make it, but would you turn to page 265 and write this down, and we're going to introduce the covalent bond. So what we've been talking about all along is ionic compounds bonding together, a metal and a nonmetal. Covalent bonds, remember what they are. They're just nonmetals, all right? But this is a covalent bond, a shared pair of valence electrons that holds atoms together in covalent compounds. Shared, all right? In ionic compounds, we give and we receive. I want your electrons. I'll give them to you. In covalent compounds, oh, it's mutual. Sort of. We're gonna talk about that at the end. But we're sharing. We're going to come together, and this is going to be a sharing relationship. All of our electrons, well, at least our covalent, our valence electrons, we're going to share. We're going to share together. For covalent compounds, molecules made up of nonmetals that always want to gain electrons and never want to give them up, the ideal electron configuration is attained by sharing, not transferring. Therefore, none of the atoms in a shared configuration always has the ideal, but each of them contain the ideal sometimes. And so next week we'll introduce how they share them, and that won't be that long a discussion. So, but you've been introduced to ions in terms of the way they come together, and now I just barely introduced you to how covalent compounds come together. We'll finish it next week.